So, we had a very nice talk from Albert on image sensors, but there are more sensors in the world, and there are even more sensors here in Europe. And I think it was very nice of Ali to think about, can we invite also companies here, and local companies to the conference to show what's going on in the world of silicon. So, my talk is about sensors everywhere. And I'm going to talk a bit about the company, but very little, because I don't have a lot of time. And then I'm going to say, how do we navigate? How does our cell phone know where I am? And GPS, that's the elephant in the room, but I'm going to tell you why GPS is not the way we work. And I'm going to talk about accelerometers, gyroscopes, all these kind of very nice integrated MEMS sensors. And then we're going to talk about other ASICs that have been developed at ICsense for indoor navigation, e-compass and barometric pressure sensors. And in the end, we're going to draw some conclusions, and there is time for Q&A. So, first about ICsense. ICsense is an ASIC design house. It's specialized in high-end mixed signal sensor interfaces. So, all about sensors. And you can think about sensors in the broad sense. Automotive, medical. We also have industrial, aerospace, and a bit of consumer. And it's about the consumer part that we're going to talk about. ICsense is founded in 2004, so we are 20 years young, let's say. And we're a spin-off company of the KU Leuven, of the AZ Micas group. And started by 4 PhDs, of which I am one of them. So, how does a company grow here in Belgium? Well, we started out, and that moment we still looked pretty young, in a small office, almost a garage. We were actually almost sitting on each other's lap. But then, after a while, 2011, we started our digital team. We already were then with let's say 40 people. And we had a lab space of 50 square meters. At 3 years, and we need to move again because we were 60 people with the 100 square meter test area. And now, almost 20 years later, we have our own ATE development lab here inside our building. And we are part of the TDK Corporation, and we're doing all the ATE development for them. So, a huge test lab. We are currently with more than 100 people, have an office in Ghent and one in Leuven. So, if you're looking for an interesting job, you know where to find them. So, navigation. Everybody tells me when I talk about navigation, they say, it's simple. Problem solved. We do have GPS. But then, let's have a look. When you move outdoor, this is the power consumption of a GPS. And this is the power consumption of all the other sensors that we have. GPS is extremely power hungry. We need to talk to satellites. And not only to one. We need to have at least 5 in the line of sight in order to find our position. GPS has a very bad reception outdoors, and certainly in urban canyons. Luckily in Bruges, every buildings are very small, but when you're walking, let's say in New York, in between the skyscrapers, then there is that much reflection of the GPS signal that your reception is very poor. And when you do the math, you have an accuracy of 7 meters at best. Now, you can tell, Tim, 7 meters, that's not that bad. Yeah? But if you want to do indoor navigation, right, that is a floor, right? Or your GPS thinks your head is through the ceiling. That's not true. Update rates are pretty low, so you cannot run too fast. Now, as Albert said, our golden reference is the human eye. So for navigation, the human, let's take the human as our reference. How do we navigate? We don't have a GPS inside. No. We have our image sensor. Our image sensor tells us there's a church, walk to it. But not only the image sensor, we also have a very good gas sensor. So if you're walking at the seashore, you immediately know where the harbor is. Just smell the fish, right? Pressure sensor. You really feel where you're heading to. You feel the wind. In your ear, you have an accelerometer. Truly, you have an accelerometer and a gyroscope inside your ear, your equilibrium system. It's very important for navigation. And that comes with a huge amount of data processing. So, let's start. Our human ear. How does this thing work? Now, an accelerometer is actually a pretty simple device. You have a proof mass, which moves around, and due to Newton's second law, right, it converts acceleration into force. And then you have these springs, and these springs, they convert the force into a displacement. And again, the formula that you need to remember from Albert, it's the same formula here, right? Capacitance, we need to measure a capacitance. Our displacement is transferred into a capacitance. So, we can measure with these structures. We measure a few attofarads. We need to measure a few attofarads. And again, noise is extremely important here. And we can reach from attofarads to micro-Gs. That's pretty amazing. And we do that for only 200 microamps of current. Now, this is a very neat device, but for navigation, there is one problem. We measure acceleration. Acceleration is the second derivative of position, so we need a double integration. Any offset error that we make, 1 over f noise, that's low frequent, it is double integrated. So offset becomes a quadratic error. But it's just one of the sensors that we will use. Now, fun fact here, basically, I made these slides, as Ali told months ago. At that moment, I thought it was a fun fact. But in the European Championships, it was not that fun fact, because the accelerometer inside here that causes 3 goals of the Belgians to be faulted, unfortunately, is coming from my group. But okay, let's call it a fun fact. Another type of sensor, the gyroscope. You not only want to know the acceleration, you also want to know the rotation. And we know that very well. It has been used in navigation for ages. So where you have this rotating ring, and you have this very complicated, let's say, suspension here. And due to the law of conservation of momentum, right, this ring always stays at the same axis, rotating around the same axis. So by having a look at how your suspension is moving, you know how you are rotating in the plane. This is a very neat sensor, and you really not only need to know where you're heading, but also your heading as such, so your angle. Now, this looks kind of complicated. So how can we integrate that in silicon? Now, here's the answer. This is an integrated planar gyroscope. Again, we are working with the same coumbs as we have for the accelerometer, because we want to read out capacitances. We want to read out, in the end, we read out displacement. So we want as much surface as possible to create as much capacitance as possible. Now, remember, we want to have the conservation of momentum, so we need to create momentum. What we do is we have a second comb here, and we start rotating or vibrating this device, hence and forth. And when you rotate the device, it starts moving up and down a bit, changing in your reading cones a bit the capacitance. So it's a planar structure, but you can measure 3D rotation with it. So one difference with the accelerometer is a pure static device. Here it's a dynamic device. So we need a drive force, we need a driving voltage in order to move it around. In this way, we are able to measure with a noise floor of a few millidegrees per second per square root hertz. And this for only 0.5 milliamps of current. So again, much better than a GPS, and it also will give us a sense of rotation. But again, we need integration to have the angle. Now, can't we create sensors, integrate sensors that have an absolute value of our position? And the most common thing is a compass, right? A compass has been there for ages as a navigation tool. It gives the absolute angle and the absolute direction. Even in systems nowadays where GPSs are used, we use a compass to improve the accuracy. You know, the first GPSs, or when you have an old car with an old GPS, you start riding and the car thinks that it's riding the complete wrong direction. Why is that? It takes a sample of the GPS signal every few seconds, and then it can discriminate the direction from these two points. In modern GPSs, the GPS first asks the compass, what's my heading? And then immediately you start navigating correctly. Now, how can we measure the magnetic field? Magnetic field is about only 25 microteslas, right? So 25 microteslas, that's the Earth magnetic field. Now, everybody has some magnets on their fridges to get your grocery shopping lists. Those are 10,000 microteslas. So you need to be very accurate in an environment which is completely unfriendly for magnetism. So you need to make sure that you're not overloading the sensor. For half a degree of accuracy, 3D, you need 200 nanotesla RMS noise. Again, I cannot say I need to claim he's right. Willy Sansa says you need to know something about noise, otherwise you cannot build a navigation device. So, how can we sense magnetism? Well, we do it with magnetoresistors. You can also do it with a Hall plate, but if you take a look at a Hall plate here, it's very linear, but it's not that sensitive, and it has an offset. So we go to magnetoresistors, and we had AMRs, we had GMRs, and now at the moment we have TMRs, tunnel magnetoresistive elements. They've been developed back then to increase the density of hard disks, and now we can use these incredible devices to sense the Earth magnetic fields. They are highly sensitive, they have a high signal-to-noise ratio, and a very low operating current, so which is very good. Now, how do you create this kind of sensors? Well, basically, it's a magnetic sensor, so how hard can it be? You put your sensor here, and you put another resistor there on the top, and by doing that, you have a very nice signal, which is a resistive divider of your supply, right? Which is dependent on your magnetic field, so thus on your resistivity below there. Now, this is a problem. The problem is basically this signal is dependent on your supply, and it's not located around zero. Zero magnetic field gives a non-zero signal. You have offsets here and so on. Very nice solution for that is basically we take a second one. We take a second one here, right? And that will give us a reference. So we measure between those 2 points, right? And then we have zero voltage for zero signal. That's something we like. Now, this system, where you have a reference device, and then at the other end, the laser pointer is not working that good anymore, and where you have your sensor on the left side, we usually draw that in a diamond shape. And then we have a very nice Wheatstone bridge, which is the way we measure these kind of signals. Now, last part, we now know how we can measure direction. Height. Height is a very difficult thing to measure. But we have something on Earth which is called barometric pressure. And barometric pressure can be used as a measure of absolute height. Because we know 1 Pascal of difference is equivalent to 8 centimeters of absolute height difference. Right. Now, when you take a look at the weather forecast, then you heard the weatherman or weatherwoman talking about current barometric pressure is 100 kilopascal. So it's a huge dynamic range that you need to have to measure these 8 centimeters. You need 17-bit of accuracy. But what is the big advantage? If you can create a sensor, and I've taken this from the workshop given by the colleagues from Bosch last year, 2 years ago at ESSERC, 2 years ago. If you can reach this noise level, this accuracy, you can even measure people walking stairs. And that's what your cell phone nowadays can do. It can even track your steps. Your podometer is working with a barometric sensor, just to measure the amount of steps that you're taking every day. How can we build it? Well, very simple. Again, it's MEMS. I say it's very simple. When there are MEMS designers here, they say it's extremely complicated, and indeed, it's extremely complicated. But just the principle. We have a plate of silicon, we have a plate of silicon, and in between, we have an empty cavity, complete vacuum. When there is pressure on top of the top plate, then we have a small bending of the top lid here, right? And again, our capacitance changes. So we need to measure capacity, right? And again, we need a resolution of attofarads. Attofarads, it's very small. But we can do that. Another problem that you have, we have again I think this laser again stopped working. So, the problem is when you are bending, I will use my hands. Albert showed me how to do that. When you want to measure pressure versus displacement, you want to have it like this. But we cannot make any plate that just goes linearly like this. What happens is you're bending your plate. So this means it's a very highly nonlinear system that we're having. So again, we need a lot of digital compensation and calibration because we need to measure all these bending moments from this sensor. Another problem that you're having is that basically you're not measuring pressure. You're measuring mechanical stress. And in the end, you need to glue somewhere this sensor, either on silicon or on a PCB, somewhere in your package. So you inherently have different temperature coefficients in your system. When temperature changes, also the stress changes. And maybe your sensor goes, instead of this, starts bending. Your displacement, again, these attofarads are changing. So we need a nonlinear compensation. And again, we need this human brain that I was talking about in the beginning. Now, how do we measure capacitances? I've been talking a lot. Every possible navigation measure that we need to take is transferred into a displacement, hence in a capacitance change. Now, oh, now I have a red light. Great. Everything becomes much clearer in red, right? What you do is basically you have your sensor, and it's a capacitance, so we need to add an AC signal to it. You cannot measure DC with a capacitance. So we put an AC signal to it. But remember our pressure sensor. It's like this, and we want to make this very tiny displacement, but there is already some resting capacitance to it. So we distract it with a capacitive DAC on the bottom here. Again, there is noise, and there is offset. We sample the offset here on these capacitances in order to get rid of those. So we have our pressure signal, we subtract our offset signal, our resting capacitance, we subtract the offset of our amplifiers, and then we put those charge from these capacitances onto our gain capacitance. And that gives a voltage which we can measure with an 18-bit sigma delta ADC. 18 bits, so you really need sigma delta. And I hope Chris will explain why you need that. Now, then I have this box. Just to end my talk, how do we integrate all of this? And how can we make this work in a mobile phone? The promise of my talk was to show you how we can do navigation in a mobile phone. Well, the only way to do that is to turn off as much as possible. Everything in gray here is only turned on at 100 Hertz. We do a measurement, we shut down everything. In that way, we can measure at 100 Hertz for only 50 microamps. We have a sigma delta converter. What's the big advantage of a sigma delta converter is basically the longer you integrate, the longer you convert, the higher accuracy you have, the higher the oversampling ratio is. So basically, if you're walking around and we want to know how many stairs we take, we can say, okay, let's do that with 14-bit, 15-bit. If you want higher accuracy, because our system, we are doing very accurate indoor navigation, we can go to 16, 17-bit. And then our power consumption scales with the amount of integration time, because we turn off everything. When we don't measure, we turn it off. So we can go 200 microamps for very high accurate, very high speed navigation. But when you do normal navigation, we can go to 20 microamps. And that's the very powerful way of constructing this system. Now, again, you see, we have I3C, SPI, we have this very huge digital part. This is team effort. And this is my final message to you. Nowadays, you cannot build any silicon anymore, any circuit anymore on your own. We as engineers, as community, we need to work together. And we work together with the MEMS people. It's also here at ESSERC. It's very nice at ESSERC, I must say. We have the device people here, we have the circuit people here. And those are the people that need to work together in the future to get this kind of systems done. And it's not only this. A pressure sensor needs to be able to sense the air. So we also need packaging people, because that's a cavity, and so on and so on. It's like Bill Bauman said in the beginning. We are no longer talking about 1,000 transistors. It's a billion transistors. And you need hundreds of people to do that, to make this. So, to end my conclusion, and I think I'm pretty well in time, went only small overtime. Navigation with a smartphone, it uses a huge amount of sensors. It's not only GPS. We need sensors everywhere. And it's the operating system of your smartphone that chooses the most appropriate sensor that you need. Based on the application, based on what you're doing, it just chooses which sensor to use and in which accuracy. A GPS, okay, we need it, but it's too power hungry to be used continuously. I've shown a various amount of sensors, not in too much details. It's only a 20-minute talk, but you remember we have accelerometers, gyroscopes, we have barometric pressure sensors, we have e-compasses, and we can all integrate them. They're all silicon compatible. And they all consume way less than a GPS. So, if you have questions, I'm very happy to answer them.
Thank you very much.